Hey, yo, thank you for coming back. You already know who it is. It's Key, aka Matter Development. And we're going to pick up where we left off in this little study series about vectorization with Python. Before we get started, you probably noticed that I have some new things going on. I have this lovely OpenPair screen here, which is the same little screen that I use for my trailer. So if you go to my channel, you'll see there's a little trailer that'll kind of give you the gist of what this series is and where it's going. And I encourage you to go watch it and also to share as well. Spread the wealth, spread the news. Sharing is caring. Okay? Anyways, if you missed the last video, just to get up to speed, we're looking at vectorization. Vectorization is the means of doing operations on matrices and vectors and things like that in Python. The reason why this is an important approach to do those things with scaling and doing various operations with these matrices and vectors is because typically if you just do it with straight up vanilla Python, it's really slow, very, 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 very slow. But with vectorization using the Numpy library primarily, we can utilize the GPU of your computer, and that will allow for the calculations to happen in parallel. That's going to be really important as we move deeper into machine learning, because we're going to be dealing with potentially large data sets. I would encourage you to go back and to at least look at the notes that I left in the description below for this video. In the description, I have a link to a article, or a little PDF rather, that I put on LinkedIn, and that is literally the same as this here. So in that PDF, I'm showing you what vectorization looks like as far as the literal code and the difference between a vectorized approach to dealing with things versus a non-vectorized. And this is in specific reference to multiple linear regression, which is going to be the next topic video little mini series after we deal with the vectorization exercises here. Okay, so yes, stay in the loop. Check out the bottom of the video to look at the description, resources, and everything. And if you feel a little bit lost, nothing wrong with going and check out that little PDF, or start with the first part of this vectorization little mini series. Okay. So where did we leave off? We left off measuring the efficiency between vectorization and looping. I'm going to run this really quick because I think it's just really, really valuable to see exactly what this looks like in terms of the time difference. So I'm going to run this right now, and you can see down here, it literally took a long time, because we're dealing with 10 million, we're dealing with two vectors that are 10 million in length, right? And so you can see here the vectorized version, whoops. Typo. Okay, you can see here the first thing that prints out is the timing for the vectorized version, 4.74 milliseconds. And then you can see here the non-vectorized version is 2,916 milliseconds. It's a pretty significant difference. Now, if you're dealing with if we were to deal with vectors that are just really small, maybe only 10 entries, then that difference, it's still a big difference by some orders of magnitude, but from an experiential wait time for us as human beings, that difference doesn't seem significant. But the more data you're dealing with, the more that those differences, that difference in compute speed, the more that matters. Okay, so if you have not watched my videos before, by the way, this particular video is a study session. So we're just going to together just get into the nitty gritty. Sometimes there's going to be some mistakes. Sometimes we might even get lost on some tangents. Okay, that's sometimes how it be. But that's what this video is for. And if you're interested in just an explanation, just here it is, this what it do, then you're going to want to come back and look for the video of a similar title, but it'll have in parentheses explanation at the front. That's how all my videos are structured. Study sessions are labeled as such, and explanations are labeled as such. Eventually, I will have two separate playlists, one for everything and one for just explanations. But for now, until I get my little video count up where it makes sense, just make sure you look at the title of the video to know whether or not you're looking at an explanation or a study session. The purpose of these study session videos is just to have some guided learning. And if you're taking this course, which is linked down below, or if you're just doing this by yourself, I think that you'll find this study session still nonetheless helpful, okay? So I'm just following along with a lab that is already pre-created, and I'm doing it over here live for you to follow along. So the next thing we're gonna do, now that we've explored the efficiency between vectorization and this looping strategy, is we're going to look at, we're going to just look at some examples of vector to vector operations. And actually, no, we're going to just do matrices. How about that? How about, yeah, we're going to look at matrices. Well, let's hold on. Let's hold off on that just 1 second. I have a little extra module here. This is basically just going to be vector operations, but it's just going to be here just exploring something, another concept really quickly. So let me make a new little block here. We'll call this miscellaneous vector operations. Whenever you see vector, what that means is you're doing an operation that involves two vectors, whether it's like dot product or scaling, multiplication, something like that. It's just involving two vectors. That's what vector means. Okay, so so when we're doing machine learning, supervised machine learning, we have X training data and we have Y training data, and we have a weight and we have a bias. And with multiple linear regression, we are going to have multiple values for X training data and X and Y training data and the weight. But not only that, but we're going to have multiple features that weight and those features have to do calculations for. So it says this will be explained in a little more context. Two-dimensional arrays. So we're going to be dealing with potentially arrays that have more than one dimension as well. So like a one-dimensional array is like, so let's just do an example of 1D, not one direction, calm down. One-dimensional array would look like this, like some number, some number, some number, some number, some number. For the purposes of this, just know that all of the entries in this array need to be of the same type. So in this case, we're going to just be doing like, this is your integers right now. A two-dimensional array would be like this. So we say 1 and 2, and then within that you do 2 and 3, and 3 and 4, and then maybe 4 and 5. I'm getting confused now. So you can see here, both of these arrays, this one-dimensional array and this two-dimensional array, it looks like these have the same size. They're both the size or length of 4, but the difference is that they do not have the same shape. So like this first one here, this would be the size or the shape of this one would be like 4, 0, or just 4 comma is how it'll be expressed in Python, like if you were to print out. And then here, this one would be like 4, 2. So the first number is just the number of elements, and then the second number is the dimension of those elements. Hopefully that makes sense. That's a lot to wrap my mind around, honestly, as I'm like doing some of these exercises. I find myself like trying to do things with arrays of different shapes, and it'll cause problems in some situations, depending on the operation doing. Sometimes it doesn't. So that's something that I kind of struggle with. In particular to what we're doing right now with multiple variable linear regression, Our weights. Okay, so in our univariate linear regression, maybe I should just add a note here. So in univariate linear regression, we have a single weight. We have a single. We have an array, rather, of one-dimensional. My language is failing me. Okay, in univariate linear regression, we have a one-dimensional array of scalar values for the input. And then in univariate linear regression, we also have a one-dimensional array of scalar values for the targets. That's the y. So this is x, and this is y. Make this a little title there. Ooh, that is too chunky. Python. Okay, so in univariate linear regression, there is a one-dimensional array of scalar values for the input x, and there's a one-dimensional one-dimensional array of scalar values for the targets y. In multiple linear regression, I'm going to show you the example here. Let me bring up. Phew. Sorry, I had to sneeze there. That kind of snuck up on me as a little bit of surprise. Whew. Oh, Lord. Lord have mercy. Woo. Relax. Woo. Okay, anyways, now that my little fit is over. In multiple linear regression, the big difference is that we'll have an array of n dimensions, and n is the number of features. So so I'll just write it out here. So we'll have an array for inputs, an array of n. I'm going to use latex here to make this special. Make sure that I render correctly. So we have an array of n-dimension features or inputs. I'll just call them inputs. That way there's some continuity with the language here. So for multiple linear regression, we have multiple features that we have to deal with instead of a single feature. And each of these features has its, the way that it'll be dealt with in code is that each of these will be of some length called m. And m is the number of items within any specific array of features. Okay. And also, also the difference is that in multiple linear regression, we have for weights, we will have an array of n dimension. Actually, no. Back up. We'll have a one-dimensional. We'll just call it 1D. One-dimensional array of. This is what happens when we try to do this live. Okay, so for weights, we'll have a 1D array of scalar values, And this will be weight. By the way, for univariate linear regression, you have a single scalar value for weight and a single scalar value for bias as well. And for multiple linear regression, there is a one-dimensional array of scalar values for the targets. And then you have a one-dimensional array of scalar values for the bias. So these are like, there's some differences here. The big difference is that the, oh wait, make sure I got this right. Yeah, the big difference here is that for univariate linear regression, there's a one-dimensional array of values for the input x. And then let me go ahead and like give some examples here, by the way. I think that'll help. So for univariate, x will be like x of 1. I should probably do this in, I'll do this in latex. So this will be like x subscript 1, x subscript 2, x subscript 3, and then so on and so forth, to x subscript of m, right? M is just the maximum, it's the size, the maximum size of this array. So for the y input, it's also the same, except I'm just going to change the number or the coefficient letter here. I don't know if that's called a coefficient. I think it's just called a variable. Okay, so the single scalar value for the weight, I'm just going to put that in latex too. By the way, latex is just the little notation that allows you to do math notation in Markdown. Okay, so similarly, I'm going to do these here, make these all uniform. Actually, I can just get rid of this. By the way, if you don't know, if you haven't already caught on, I'm really big on note taking. I love to share my notes, but if anything you walk away from, other than that I'm a crazy person, note taking is really important because your note taking is going to be your personal cheat sheet. So I treat it as such. I always take the time to make my notes as neat and as organized and as thorough as possible so that I don't have to like spend a lot of time reading weird documentation on the internet, because sometimes people don't be explaining things in a helpful way. So when I do like my own study sessions, I'm trying to put things into my own words and to explain them for myself so that it's more easy for me to like reference rather than going and reading some obscure documentation. That's my little soapbox here. Okay, so for multiple linear regression, the example of the inputs for the in-dimension in dimensions. Okay, so the example of the inputs for the features, which is also called x, that's going to potentially, it can have different dimensions, because like we don't know how many features. Regardless of the number of features, it's going to be treated the same. It's going to use the same like dot product method, but the way that it looks, it can change. So I'm going to just give an example. I'm going to take this example here actually. Pop that right here. And what I'm going to do is I'm going to call this so one thing to know is that when we're talking about the features versus the index for a feature, we delineate them by using a subscript and a superscript. So Let me try to find an example. I might just have to do this manually. So let me go ahead and just do this manually. So I'm going to do it the subscript way first, and then I'm going to show you how the superscript separates each of the elements so that they're indicating their own dimensionality. So the subscript is going to be like x of 1, and then x of 2. No, I'm sorry. X of 1 will be x of 1, and then it'll be x of 2, and then it'll be x of 2, x of 2, x of 2, or I'm sorry, confused, x of 3. If you want to know what I'm doing, I'm just looking at this here, right? So in this example here, we have 4 different features: x of 1, x of 2, x of 3, x of 4. That's what I'm doing right now. Okay, and so the other thing is that we want to make sure that each of these features has its own, so this x of 1, this is like the J, this J symbol here. This is noting that this belongs to the first feature, the second feature, the third feature, the fourth feature. Now each of these indexes within the feature is going to have its own denotation, which will be like this. Let me just zoom in. I know this looks a little ridiculous, but this is the way that you'll see it. So this is x of 1 with index of 1, x of 1, index 2, and then it'll be similarly for the other one. So x of 2, index 1, x of 2, index 2. Now, you don't actually have to do all of this like the thing I'm doing right now, but this is a valuable thing to at least like understand, even if you don't go out and manually do this, because this is under the hood. And also, like, if you're into the math part of things, this is like the actual thing that you have to think about if you were doing this in your head or on paper manually. Luckily for us, when we program, we don't have to do LaTeX because it's a little dense. But it does help to kind of like understand exactly what's going on. And the big thing just to know is that like this subscript J, it indicates the number or the actual feature. So these are individual features, and then the superscript, it represents the index within these features. So for this example here, this is a two-dimensional array because each of these elements has 2 items within it. So in dimensions in this case is 2. I'm sorry. I got this confused. The in dimensions, I'm sorry, what in dimensions represents is the number of features. So in this case here, let me just go ahead and put it in my notes here just to resolve any confusion. So in this example, the array contains 4 features. So that means that n equals 4. Okay, and in this example, the array contains 4 features, and every feature has a size of 2, which means that m equals 2. And all of these will be uniform because they need to be in order for our operations to work. Okay, so in this example, it is as such. When I say in dimensions here, I think maybe the better way to understand it is that you could be working with a data set where you don't know. Work with a data set where you are going to perform operations on an unknown number of features that correlate to a target. So N is the number of features. So N is the size of the feature list. So for inputs, an array of size N with dimension M. Okay, my bad. That's what happens when you do stuff live though. Sometimes there's mistakes. Okay, so just to come, and I'm gonna come back and talk about this stuff after I've finished messing up live here in an explanation video. Just remember that, so don't judge me. Please don't cancel me. Okay, so you can work with the data set where you're going to perform operations of an unknown number of features that correlate to a target, target Y. And N is the number of features. M is the number of items inside the feature. So, yes. Okay, so I guess kind of going back here just a second. What I was saying before is that the main difference between your univariate linear regression is that you have a one-dimensional array of scalar values for your input, one-dimensional array of scalar values for your targets. These two are going to be the same. The only difference is that one is the input and the other is like the training result that you have for each of those inputs. And then you have a single scalar value for weight and bias that gets applied across all of these inputs. Whereas with multiple linear regression, you're doing what's called a dot product, and that dot product means that you need to have a array of scalar values for your weight, a one-dimensional array of scalar values for your weight, which will look like this here. And that's going to be applied to each of the features that you have and to each of the items within those features that you have. And then you still have a single scalar value for bias. You have a single scalar value of B. This will be covered in the next video with multiple linear regression, so no need to understand all of this right now. Oops. One thing that's really tricky about machine learning stuff though is that a lot of the variables and the code and everything, it's very arcane in the language that it gets used. Like if you do stuff with like app development or database stuff or stuff like that, you're probably used to variables having like more clean code style naming conventions, whereas the variables and whatnot for like data analysis and statistics and like machine learning, they're kind of like based on like really abstract math concepts and math notation. So the way things are named is kind of meant to accommodate for the fact that you don't always know the what that you're dealing with, but you still have to build an algorithm that can be applied to a variety of types of data and whatever. So everything's just like a lot more abstract, and it can be really hard to internalize your understanding of what's going on, but even more difficult to communicate it. So hopefully that kind of helps if you feel like this is a little bit obscure. Okay, so let me just make sure here. One dimension. So weight would be a one-dimensional vector of shape n. So I guess shape n is important. Because shape n just means that the length of this array for our weights in multiple linear regression needs to be the same length of the feature list for our inputs. And the same thing is true for our y outputs as well. And I'm going to go ahead and denote this up here of size m for univariate. Sorry if you can hear the cars in the background. I feel like I apologize every episode, but one day y'all gonna learn that I live in a city. I'm a city boy, so there's always some noise going on. Just grateful that there are no amber lamps in the background, because that sometimes it'd be like that too. Okay, so this one-dimensional array of scalar values for targets of shape n for multiple linear regression, I'm going to denote this similarly to how I denoted the x feature list as well. So each of these are going to have an index. Oops, score 4. And actually, yeah. Each of these is going to have an index. I think that's good enough for now. And the reason why these indexes matter is because when we're doing dot product operations, this index of 1, this y of 1, and this x of 1, x2 of 1, x1 of 1, and x2 of 1, these are going to be paired, right? And the same thing is true for our weights as well. Our weights will correspond to the appropriate input with the same number here. I'm going to call this, I'm going to use the same, I want to try to make sure the language is the same. That's bigly important to me. Look, we haven't even gotten to our little exercise down here because I'm just being picky. I'll be thankful that I'm doing this later on now. Okay, so now we have, looks like here we have some examples of what vector dot product operations kind of look like. So I'm going to just write this here. This is a common example of something that will be occurring later on. np.array is just our method of creating an array using Numpy, which gives us access to the ability to do vectorization. Vectorization does not work with just straight up vanilla Python, by the way. It will throw an exception and then you'll cry, because I cry. So I'm sure that you may cry as well when it doesn't work. It's a sad day. Okay, so one thing, by the way, is that when you make an array in Numpy, normally you can just pass in like something like this, and it will be explicitly understood as an array of 1 dimensions with the shape of 1 comma. But what we're going to do right now is we're actually going to pass in each of these as being its own array. We're explicitly defining the shape of this array. Now, I don't know exactly like how that differs, so I might stick around and play around with that just for a brief second. We're gonna make another array with just 2 here, and then we're going to create a variable to hold the dot product of these 2 arrays. So, oh, I forgot to add this. So what this means here, this means that, I got a graphic here. Dot product just means that we're taking 2 arrays and we're taking the indexes of each of these arrays and we're multiplying them by each other. And then we're gonna do a summation along the entire length of both these arrays, which in this case is n. So by the entire length of both of these arrays, each of the indexes get multiplied, and then that summation is C. So that's what's happening here. This is A, this is B, and this is C. Can y'all see that? Okay. So I'm gonna print this stuff so we can see it down below. We're just gonna print the shapes. Has shape of this x of 1 here. What this means is that for this x variable, we're going to be looking at this here, everything that's within here, because in theory we could have multiple things going on. Actually, pause that. We're just going to play around with it, and then I'll be able to show you rather than just explain it to you, because I don't want to tell you the wrong thing. This is a study session. Okay, so print, we're going to do the same thing for W. Has then we're going to do the same thing for C. Oh, excuse me. Okay, so C has a shape. What I would like to see as well is I'm going to print I'm going to print these so I can actually see what they are. Okay. Whoops. So we're only doing this for a specific index, by the way. We can do this for the entire array, but I guess this example that we're doing right now is just for an index. And we're just experimenting with the dot product of one specific index. So up here, it would appear in this example, we would just be doing it with the second index of both of our arrays, A of 1 and B of 1. Or in this case, it would be, we'd be doing it with this x of 1 here, which is the first index, and then we'd be doing it with this W, which is just 2. And I'm gonna see if this actually throws an error here in a second as well. But I don't think I need to print the other ones since they're evident. Well. Let me go ahead and do it and stop being lazy. Because I think if someone were to look at this for explanation later on, it would be a little bit confusing if I didn't. Okay. And then something here. Okay. Now, one thing we could try to do that would betray our, or I could actually just do it down here separately, is if I were to do this dot product again, let's just call this one C2 or C_2. And I was trying to do dot product with all of X, but to do that with the weight, I want to see if that actually will work. I don't think it will. I don't think it will, but let's give it a go. So I'm gonna call this C_2, C_2. Oh, it did. Okay. So I could explain why it worked, I suppose. So in this block here, what we're doing is a dot product of X. We're multiplying it by, so if we were to treat X as being its own array, its own vector, and we're going to multiply this vector by this vector here, then what we get is 1 times 2. We get an array that has 1 times 2, comma, 2 times 2, which is 4, comma, 3 times 2, and 4 times 2, which is this here. So these do not need to be the same lengths. I'm just going to put that in my notes here as a comment. The vectors for dot product do not need to be the same length. The operation will multiply the two vectors to create a length of the length of the output would be the length of whatever vector is the largest, basically in this case. And then this is the dot. This first one is the dot product of two arrays with single scalar values. Okay. Where I think this might break, and I'm just going to see, is if I wonder if these had a dimension of 2. I wonder if this would still work. Now, I don't, if it doesn't work, I'm gonna be sad, but this little experiment, yeah, I was expecting it won't work, because even though this whole thing is a vector with the same size as we had previously, the shape doesn't match. So I think if I did like this, it would work, because we're essentially multiplying this shape vector by these elements which have the same shape. But you cannot do it if one of them does not have the same shape. So I'm actually going to, I always do that. Okay, I'm actually going to take this here, and I'm going to make a comment down below, because I was actually a little frustrated yesterday. If you remember watching the part 2 to this series, I was trying to do that yesterday. I was like, why ain't this working? This is trifling. I'm mad. I'm gonna call the cops. I was trying to do that yesterday and it didn't work, and now I think I understand why. So let me just put here vectors must have the same shape to work. And then I can put in my notes here, the above won't work because for dot product, and I actually need to copy this thing right here. The above will not work because for a dot product to, the above will not work because the vectors, because even though both vectors array, because even though both arrays have, no. So dot product doesn't require the arrays to be the same length, but the items within the vectors need to have the same shape. In this example, I'm going to call them elements. In this example, the elements of X have a shape of 2, and the elements of W, the element of W has a shape of 1. And separate these out. I always do that. Okay. Why is this so chunky? Oh, because I'm zoomed in. Okay, so I think I have what I need there. I'm glad I got this figured out, because yesterday I was actually a little bit confused, to be honest, which is pretty normal for me. And this cell is in the wrong place. How do I move this up? I don't know how to move my cells around. I'm just going to copy and paste it. This actually needs to go here. Right there. And we're going to call this parallelism. Did I spell parallelism correct? I think I did. Hopefully. Embarrassing. Okay. So I think I'm good here. I feel like my little titles. Okay, I think I have consistency there. Well, I think we are ready to move on. I don't know what's more annoying, the inability to have auto completion for the web GUI for Jupyter, or the fact that I keep accidentally deleting a whole cell when I'm trying to just undo. Like, both of those are equally annoying, but that's just sometimes how it be. Okay, so the next thing we're gonna do here is we're gonna look at matrices. We're gonna enter the matrix. And we're getting close to being done with this. I think we might be able to finish this today-ish. Yeah, I think we might be able to finish this today-ish. We're gonna try. I have a little event to go to later on, so I might need to pop in. But I'll just tell you this, whatever I don't get done today, I'm just gonna cut the losses. But I think that we should be able to get a decent amount of this done. But I will for sure come back and do the recap of this in its own video. Just because I don't think there'll be enough left over. If I don't finish this, there won't be enough left over to come back and do a whole stream just for that little bit at the end. So I'm gonna take a quick little break here. If you're watching, thanks for coming by. Go ahead and grab you a good old sneaky snack. That's what I call my cat, snacks. I call them sneaky snacks. And now I have adopted that language for human usage, apparently. So yes, go ahead and grab a sneaky snack. We're going to be doing matrices. When we come back, we're going to be talking about creating and utilizing matrices, what they are, and just give me like 10 minutes. Okay, stop rushing me. Just stop rushing me. I'll be right back. I promise. And while I'm gone, you can look at my lovely artificial intelligence artwork. Are you still with me? Are you still with me? Are you still with me? Okay, I'm just checking. Just asking for a friend. Okay, so now that we're back, let's go ahead and jump back into looking at matrices. Let's go back into the matrix. Matrices are basically two-dimensional arrays. So in this example here, I was showing you this two-dimensional array that has an n of 4 and an m of 2. That is a matrix. Matrices are two-dimensional arrays. Let's make that build in live. Oops. Okay. So matrices are two-dimensional arrays. The elements of a matrix are all of the same type. So here, these are all of type integer. That is necessary in order for us to do the operations, like in this example. If they're a different type, it's just not going to work. But you can do things inside. I tested this out yesterday. Like, you can do things inside of a matrix in order to make these, in order to coerce. So for example, if I were to take, let's just change this one here, for example. If I were to put a character in here, like the character A or S, because I had a typo, I'm just going to go with it. But if I did that and I did like ORD and I changed that into a Unicode number, it would still work. You know? So you can do things to coerce the type, but whatever that resolves to, the whole matrix needs to have everything of the same type at the end of the day. So that is like a requirement here. Every element within a matrix needs to be the same type. The elements can be coerced or manipulated, or you know, I'm gonna leave that out of here. I think that's pretty self-evident. Just the elements need to be resolved to be the same type, no matter what you're doing with them. Okay, so in notation, matrices are denoted by a bold letter such as X, which is why it is a capital X here, as opposed to a lowercase. Let me zoom in just a little bit for your viewing pleasure. So yes, a capital X here. Let me get this in some latex. With a capital bold letter such as math, BF. That's how you do that. X. Such as X. Oops, needs to be capital. So yes, this is how we're going to indicate that something is a matrix. A vector would just be a lowercase version of that. Well, a vector is one dimension of some number, some range, and the way that we indicate a vector, just for the sake of comparison, is with the little arrow above it. So a vector is indicated such as, and in latex that is, what is that again? VEC, vector X, lowercase, like this. I'm going to make this large so that's more visible. Like this. I guess I should make this large too, I guess. Why not? So big bold capital X or whatever letter is matrix. and then lowercase letter or whatever with an arrow on top of it, that means vector. That's pretty consistent across math, by the way. Okay. So for this situation, m is the number of rows. Oh, actually, let me grab this image here. There's an image that I think will be helpful for understanding what a matrix looks like. This is not my image, by the way. This is one that's provided by the Coursera course. So please don't walk away from this thinking that I made this image. And I try to let y'all know when something is not made by me. Just because I'm not trying to get sued. I'm not trying to get sued. I'm trying to get, I don't know if they can do copyright strikes or whatever, you know, for images, but I'm not going to figure it out, you know, so I'll let y'all know. No, I gotta get the image. So give me just 1 second, okay? Just calm down. Give me a second to get the image. Where do it be? Where do it be? Off the screen here, I have this stuff here, but y'all can't see it. So it's called Lab for Matrices. Lab for matrices. There we go. Okay, so download that. I'm gonna pop it in there. I'm gonna take the relative path and should be the same, but whatever. There you go. Okay, so yeah. So this is what a matrix looks like in like math. Not so much the movie. If Neo was trying to escape this, that would probably be a much more interesting storyline for the 4th movie. But we're not going to talk about that. We're not going to talk about how disappointing the Matrix Revelation or whatever it's called was, even though I've seen it 6 times. But that's neither here nor there. In math, this is what a matrix looks like. I'm gonna put this in its own thing so it doesn't go away every time I'm gonna edit the notes above. So this is what matrix looks like. A matrix is 2-dimensional in size. Something about that seems wrong. Let me, It's funny, whenever I Google matrices, 3D matrices, I get like, the matrix. Okay, so matrices are 2 dimensions, and the dimensions, it's going to be a size, it's going to be a shape, basically. That's the 2 dimensions, the size and the shapes. And when you are doing like dot shape, it's going to give you this here. So for example, and I can actually do that down here to show you, because I be getting confused with the terms, dimensions, elements, items, indexes, all this stuff. It be so confusing to talk about, but it's best to just internalize this as code instead of trying to get the language perfect. It is truly a little bit confusing. So the way that this is going to look when we say it's a 2D array, I'm gonna make an example here. So matrix, 2 dimensions, m equals, what did it say? M equals m equals 4 and n equals 2. There's a bit of a weirdness in terms of how Python, like the code, refers to the shape. So like if you were to get an error, it would actually refer to this n as being the dimension, and it would assign a number to it, which which is a little bit confusing because here I'm saying that it's two-dimensional. Just know that it's better to just understand like what's going on here than to try to resolve the language, because there are sometimes some significant differences in the language used in programming versus in math. That's one of the things that makes it really hard, by the way. So this right here, this matrix here, this is going to be our example. And if we do print formatted print of matrix x dot shape, you'll see here 4, 2. So there are 4 elements, and each of these elements has a dimension or size of 2. I think there's like another way that I can get more information. I thought, oh wait, is it this here? I just saw it. I just saw it. Let me see. I think there's like a method on the array that might be able to print out some more information. Let me just check NumPy. NumPy array methods. Oh, array objects. That's what I'm looking for. Attributes, I think that's what I want. Okay, so for the sake of NumPy, the size, oh, here, I'll do a print for each of these little attributes. So let's just call this NumPy attributes, array attributes. So shape of matrix X, and then we'll do now we'll get the dimensions of matrix X. So that's n dim, which is 2. So hopefully you're looking at this versus what I'm saying more, because like I said, there's some things that are described differently between like the math side and the programming side that are a little weird. There's one more Um, there's one for this 4 here. The 4 is the number of elements in this. Trying to figure out what that is called again. I think it's just item size. No. Oh, wait. This is the number of elements in matrix X. So 1, 2, 3, 4, 5, 6, 7, 8. And what is the other one? There's just one more that is going to drive me crazy. I'm just going to have to tinker and do all of these until I find the one I'm looking for, I guess. I know it's not strides. Yeah, I don't know what strides means, but I know it's not that. I know it's not base. Yeah. Oh, this is interesting. So this dot T, this splits the, this transposes the array. The transposition of the matrix of the elements in matrix. That's interesting. I wasn't expecting to get that, but that's cool. That's a little bonus, a little stretch goal, extra thing there. I'm gonna put this at the end. Now, which ones have I not done? What does flat do? What is flat flat? Okay, I don't know what that means, but that's not what I wanted. There's item size. What was that again? I don't think this is it, but okay, yeah, that's just telling about the type of the individual elements here. The individual items, not elements. Okay. Wasn't there like a way where I can see all of the, there it is. The way I did that, by the way, is if you just put in a dot on some object, it'll just automatically give you a list. I'm trying to see if there's anything in here that will specifically give me the, oh, I'm being weird. It's just shape, or it's just length, lean. I think I could do that. No, I can't do that. How did I think I have it in my notes actually. I think I did it here in my example. Oh. Nope. I gotta go to my notebook. Yeah, I can do dot shape and I can pass in 0. So that'll give me the number of elements. Yeah, so number of items in the number of columns is what I'll call it. Number of columns. So each of these is a column. And each of the things inside these columns, these are elements. See, elements, columns, items, like the verbiage is ridiculous. Is very ridiculous. Hence why taking notes is important, because you might have to just resolve your own understanding of these things and be able to have conversational proficiency, or at least the ability to just do the do, because the language be the worst part for reals. For reals. That's one of the things about programming in general, and like even mathy things. It's like, it's the symbols are really what hold the meaning. The ability to talk about it is kind of secondary. Like for example, if you were to see like a math symbol like this vector x, how do you Google that? If you don't know what that means, how do you Google it? Like, how would you go and read a physical book and figure out what a symbol means in math? Like, that'd be the problem, is that it doesn't always correspond to like verbiage, because it is in and of itself a language. But I kind of like it, so. I'm a glutton for punishment. Apparently I'm a glutton for punishment. Okay. There's some other methods in here. I'm not going to get too crazy. I'm not gonna get too crazy. So I want to print just like a line though, so that my output here is just like a little easier to see. How to print a empty. I think it's just \n like this. Does that work? Oh yeah. Okay, I feel dumb for just thinking I didn't know that. Okay, so yes, this, nobody asked for this, but I did it anyways. Now it's there. When you get these notes, you're gonna be so happy that I've just like hit my head against the wall on your behalf. So yes, you're welcome. You're welcome. This is my sign of love for you. Okay, so now this here, what they're showing us here in terms of the notation for how we talk about, or how we visually describe the matrix, their way differs from the way that I have here. In fact, this course, which is linked below, the Coursera course for this, they actually describe it like this. So I'm just gonna put a note here. Ooh, excuse me. I'm gonna call this ways to notate matrix columns and elements. Let's just call it that. Ways to notate matrix columns and elements. The first way is like this. I'm gonna center this. Okay, so I didn't like the way that looked. Okay, so this is the one way, and this is with super and subscript. And then the other way that we can do this, which is in this image down below, this is with just subscript. And one thing though is like, I would actually recommend doing it the super and subscript way, because if you were to do double digit numbers, this way of doing it with just the subscript would be a little bit confusing without parentheses. You see how like, oops, my bad. I gotta put these in brackets as well. One second. Gotta put these in brackets. Anytime you have more than one character following a sub or superscript, it requires a bracket, or else it will treat the second or whatever's beyond the first as a separate thing. Okay. So right here, right, this looks like 12, 11, 12, 21, 22. Now, I know that these subscripts are just individual indexes for the column and for the element, but like if you didn't know that, that would be like really confusing. So what I'm gonna do actually is just put these in parentheses here, just to make my notes clearer, but you know, do what makes sense to you. Parentheses can also be confusing because sometimes parentheses represent multiplication. Context is really important. I guess that's really the theme of what I'm saying, is context is very important. But I'm doing all of this so that you don't have to, even though you should. Okay, almost done. Grinding this out, we're gonna be so thankful in like 2 to 3 months, really 3 to 6 months maybe. We're gonna be so grateful that we're grinding out these like little annoying, like little nitpicky details, because this is going to give us such a nuanced appreciation for how we can approach a lot of this stuff from so many different approaches with math. Math is, if you really think about it, it's a creative language for describing things that are extremely abstract. And just like how you can construct a sentence in natural language and approach it from different angles, sometimes you can use inversion of the sentence structure, for example, like the way that Yoda does. And you can still understand it. That's how math is. Sometimes math has multiple ways of understanding the same thing. Okay, so we put these in parentheses, kind of following this pattern right here. The parentheses are mostly important when we're doing, when we're treating these, when we're treating each of these subscript items as being like potentially different types of formulas or things. And remember that this n-1, n-1, these are in reference to summation upper limits. So don't get confused by that, by the way. Let me go ahead and add a little bit of extra context just to describe the pattern that we're seeing in both of these. So the pattern of this super subscript is x with a superscript of I and a subscript of j. I represents the column. I'm sorry. I represents the row. I'm sorry, the row, and then the column within the matrix is represented by j. So I guess I should put this here. I represents the row, and j represents the column. Capiche? Let me, oops. Oops. Move this over like this. And I think now I can actually center this and it will look decent. Y'all remember, I always say this, I like my notes to be cute. My notes to be cute, pretty, organized, and beautiful. I'm not playing. This is serious business. This is serious business. I came to slay. Large. I came to slay. And we might make this large as well. Okay. And I think I can just do like this. Okay, so we're gonna do the same thing for the subscript. Let us not leave it out. Some brackets on here. Large. Cool. Okay, so I'm just gonna copy this here. Boom, bap, boom, shabap bap. Oops. Okay, so the pattern here that we're observing in what we're seeing down here in this image is that it is X with two subscripts. The first one represents the row, or yeah, the first one represents the row I and J. I think it's already good. Nope, did I miss something? Oh, I got a bracket around here. Tab is off. And what am I, oh. What am I missing? Stop messing with me. Okay, is that it? Oh man, I haven't got myself all confused. Oh, you know what? Yeah, let me go ahead and put these two in brackets. I had them separate. That was the problem. Okay, so yes, the pattern is X of I and of J. So these two mean the same thing. I guess before I get too far ahead of myself, I'm just gonna literally kind of state that down here. Just to make it very evident for myself. Y'all, this is how I actually study. Like, I am not kidding. And I equally can be like a crazy person when I am like reading a physical book, because I do, my version of this in real life is to have a notebook where I like go through it. I wish I had an example. I wish I could show y'all. Do I have a notebook around me? Is this one of them? Yeah, I have. Oh, I can't show you that. My actual study notes be just as ridiculous as like this. I am big on like multiple color highlighters. I at times find myself like literally copying the majority of the words I'm reading as I study something. I'm really big on like breaking things down. I mean, this is just how I learned math and programming when I was in high school. My teacher was all about doing it by hand, taking intense notes, really questioning and organizing it physically and in your head and visually as the best way to get like a complete understanding of what you're talking about, or at least to expose what you don't understand. Because that really is it. Like, you don't have to understand everything, but you do want to know where like your blind spots are, where the holes are in your understanding. Let me check the time here. Okay, I got about 15 more minutes. I think I can get through a decent amount. I always say that. Okay, so these two notation are describing the same thing. I'm gonna put a little star there. These two notations are, actually let me make this a note. These two notations are describing the same thing. Okay. Yeah. Isn't this like so beautiful? Look how beautiful all this is. It's so beautiful. So beautiful. And you know, the best part about it is when I'm done taking this course, since I wrote all these notes myself and my notes are pretty independent, I'm going to just put all of this up for y'all to have for free. I mean, you still want to take the course, of course, but I'm gonna put all this up for free. I'm gonna take out stuff like this, or at least I'm gonna have to do my own version of this type, like these images. But I don't use a lot of them. I think this is only my second time using an image. But yeah, I'm gonna make all this available to you for free. That is my MO. Okay, so Numpy arrays. Numpy's basic data structure is an indexable n-dimensional array containing elements of the same type. How do I say that? So the basic structure for Numpy arrays, gotta make this markdown so it stops giving me red lines, is n-dimensional, containing elements that are all the same type. And then the way to get that type in code is x dot, what is it again? D type. One second, I just need it. Yeah, it's x.dtype to get the type can be referenced by or with. Okay, so x.dtype is how we would get that in code. Yeah, all of these need to be the same. If you don't, I think I already talked about this earlier, but if they're not the same, they can be coerced. Like if you were to analyze a character and turn that into a Unicode number, I think it's what it is, a Unicode number, then that would be essentially an integer. But otherwise, they do need to be the same type. And also another thing too is that when you see I and J here, I can also be considered M. I can be considered M because M, I can be considered M minus some number, or how do I say that here? How do I say that? I might leave that out. That could be a little confusing. I don't think I'm saying it right. What I'm trying to say is like the shape. The shape of a matrix is this. M n. M is the size of, or the number of features, like in multiple linear regression, it's like each of these columns. So the number of columns, M, number of columns, and then n is the number of rows in a column. That's what I'm trying to say. The shape of a matrix is Mn. And so when we see this in code, it'll be this here, except, you know, and also too, in Python, it'll just leave it empty if the number of columns, or if the number of, how can I say that? So like you see here, this is just a matrix of one dimension, meaning that there's only one column. If there's only one column, it's going to leave it blank like this. I don't know who made that decision, but they need to go to jail. They need to be in prison and locked up, because that is just weird. They could at least have bothered to put a 1 there. You know what I'm saying? But it's going to be blank like that. And also when you're referencing, if you're referencing like a 0 dimension or 1-dimensional array, you reference it with, like if you're doing dot shape, you reference it with 0. This is in the weirdness category of things. There's some things that you probably would only know from doing these kind of exercises, and it does become a little bit like, it would be annoying to not know this stuff more so than it is to know it, but it is definitely annoying to know it. Okay, so okay, so it says here that doing operations and stuff on matrices is not going to be super integral for the rest of this course. But matrices are used to hold training data, and training data is m examples by n features, creating this array that we just described here, or this matrix we just described here. For this video series, expected to deal with columns that could exist as part of a matrix. And for this, actually not for the time verses, but just for this, because we're going to be doing like other stuff outside of this course too, so I don't want to make it seem like that this video series is limited. So just expect to deal with columns that exist as a part of a matrix. Just as a quick side note, there are other libraries like pandas that will allow us to hold like what are called, I think they're called data sets. Data sets and series, which are like database objects that get held in memory, and those are the actual things we'll be using. These arrays and whatever in Numpy, it's a part of that, but there are other ways that we can get this data that are not databases, and they get converted into matrices, or matrix operations happen on them because they're compatible with Numpy. So just know that what's important here is that these matrices, the purpose of them isn't that we're always going to be creating them explicitly, but that we will have some data to deal with, and we want to perform our regressions against that data, but we need to have a data structure to facilitate that. And then what we'll be able to do when we have these matrices, we use them to create data structures and for slicing and indexing. And we're going to be doing slicing and indexing. What I'm going to do, like I said, I'm not going to have time to do the rest of this in this video because I have to go to this event here upcoming. So I'm going to finish out the rest of this. I'm going to do matrix creation. I'm going to do operations on matrices. And I'm going to do, within the operations of matrices, I'm going to do some slicing and some indexing. That's all you're going to be missing from the live version of this. But remember, I will come back and do an overview explanation thing over this entire thing. And in that video, I'll be just kind of summing up the part that I didn't get to in this stream. So don't fret, don't worry. Just come back, hopefully in a hurry, and then we'll have a good time. So yes, as always, I just want to remind you that this video series is here just to be helpful. Think of me as your little pair programming partner. That's why it's called OpenPair, so you don't have to feel alone. Because I know that sometimes it be like that. It's so hard, especially once you get past the elementary topics in programming. It can be very hard. It can be very lost. And if anything, I just want to show you that it is not meant to be an easy thing all the time, but you just have to get in there and do it. And I've been programming and coding and stuff professionally for 5 years. And even before that, you know, I was tinkering around and doing things on my own. And it is always just a little bit weird. It's always a little bit confusing. It's always easy to get lost. Sometimes I look at documentation and code and I'm like, what kind of wizard, you know, like elvish language am I looking at right now? Because this is a little crazy. That's how it be. That's how it looks. That's how it feels sometimes, you know. So if anything, I hope that this video series just helps you know that you're not alone in your journey. No matter how senior and experienced you get, for a lot of people, it just never ceases to be a little bit awkward. You know, that's just how it is. So one thing you can always do is go down and check the video description for this channel, where you'll be able to find some useful links. That list is going to continue to grow. I'm going to be just adding free, mostly free, but sometimes resources that you can even purchase. The course that this is based on is listed as well. Just check out any of those. The ebook for data analysis of Python is a great place to start if you want to get just into the language details, whereas machine learning for humans and the Coursera course are going to be more specific to the overall direction and content, at least this portion of the playlist. And if you have any questions, feel free to reach out to me via the comment section below. You can also go to LinkedIn. LinkedIn's great because if you follow me on LinkedIn, I always post the links to my videos, and I always post the links to, actually post the actual notes, the same notes that you see over here, because I know y'all be looking. I know y'all be looking at my little cute notes over here. If you ever want to get my notes, I post these on LinkedIn too. And I try to post them in the video. So this particular topic, vectorization, the link is down below as well. Okay, so without further ado, I'm gonna let you go because I got stuff to do. I got places to be. You know what I'm saying? I'm booked and busy. I'll catch you later. Things are coming by, and part 4 will be the explanation, and then we'll move on. So thanks. Catch you later.